Welcome to the Explainer. Have you ever really stopped to think about what's happening under the hood when you ask an AI a question? Well, today we're going to do just that. We're going to trace the incredible journey from the words you type to the complex, almost human-like answers you get back.
So this is the big question, isn't it? How on earth does a machine go from just a massive jumble of text from the internet to something that can actually chat, reason, and even create with you? We're going to demystify this whole process step by step and give you a really clear blueprint for how this tech actually works.
Here's our game plan. We'll start at the very beginning, how a machine even learns to read. Then we'll get into the model's brain, the attention engine, and see how all the pieces get put together. From there, we'll look at how it learns, how we make it useful, and we'll finish up with the big question that's driving the whole industry.
All right, let's dive in. First things first, we have to deal with a fundamental problem. AI models don't speak English, or Spanish, or any human language. They only speak one language, math. So our very first step has to be a translation.
This translation happens in a neat three-step pipeline. First up is tokenization, which just breaks our text down into smaller, manageable chunks. So a word like running might become run and ning. Next, each of these unique little chunks or tokens gets its own ID number from a massive vocabulary list. And finally, and this is the key part, that ID is used to look up a special list of numbers called a vector or an embedding. This vector is what mathematically represents the token's meaning, and it's what the model actually works with. Okay, but hang on. There's a massive hole in this plan. If you just turn words into their numerical meanings, you lose something absolutely critical, their order. The model just gets a jumbled up bag of meanings, with no idea what came first.
And that is a huge problem. I mean, look at this classic example. The words are identical, so their meaning vectors are exactly the same. But just by flipping the order, you completely change the story. A model has to be able to tell these two apart.
The solution is actually pretty clever. We simply add a second vector right on top of the meaning vector. We call it a positional embedding, and its only job is to describe where that token is in the sequence. And here's the really cool part. We don't tell the model how to represent position. It learns the most effective way to encode it, all on its own during training. So, now our model can understand individual words and their order. But how does it figure out how they all relate to each other? The context. This brings us to the absolute heart of the whole system, the breakthrough concept called the self-attention mechanism. So, how does this whole attention thing work? Well, for every single token in our sentence, the model creates three brand new vectors. The first one is the query vector. You can think of this as the token asking a question to all the other tokens. Hey, what do you guys know that's relevant to me right now? The second one is the key vector. This acts like a little label or a signpost on every other token announcing what kind of information it has. It's basically the potential answer to the query's question.
And finally, you have the value vector. This contains the actual information, the real substance, that a token will share if its key is a good match for a query. So the model is constantly comparing every token's query with every other token's key. The stronger that match is, the more of that token's value gets blended into the final output. That's literally how it decides which words to pay attention to.
This system is super powerful, but it needs a little safety valve. See, when the model is calculating how well all those queries and keys match up, some of the scores can get really big. This makes the model overconfident and basically stops it from learning. So we do something simple. We just scale all those numbers down. It seems like a tiny tweak, but without it, these deep models just wouldn't be able to learn effectively at all.
Okay, but this raises a new problem, right? When the model is generating text, we can't let it cheat by looking ahead at the answer. It has to predict the fifth word using only the first four. So how do we stop it from peeking into the future? The solution is just incredibly elegant. It's called a causal mask. Before weighing the importance of any words, the model just assigns an impossible score, think negative infinity, to any words that come later in the sentence. When the math gets calculated, that impossible score turns into a 0 probability. It's like putting blinders on the model, making any future words completely invisible. Okay, so we've got our context-aware attention engine. Now, how do we stack all these pieces together to build the deep network that makes modern AI possible? The fundamental unit is called a transformer block. Each one contains our attention engine, but it's multi-head, which just means it runs the same process multiple times in parallel to find different kinds of relationships. After the attention part, all that information flows through a simple feed-forward network, which just does a bit more processing on each token by itself. A real model stacks dozens and dozens of these blocks. The problem is, as information passes through that many layers, the original signal can get lost, kind of like a game of telephone. The solution is called a residual connection. Think of it as an expressway that lets the input to a block take a shortcut and get added directly to the output. This ensures that original signal never gets lost, allowing the network to become incredibly deep without breaking down.
So, we've built our entire architecture. But what is this massive, complex machine actually learning to do during its initial training?
Well, the task is actually shockingly simple. It has one single goal: predict the very next word, or token. You give it the quick brown fox, and its only job is to predict jumps. It does this over and over and over again on trillions of words from the internet. And by being forced to get really good at this one simple task, it has to learn grammar, facts, context, and all the subtle patterns of human language.
And when you apply that one simple task to a model of this scale, even a relatively small one by today's standards like GPT-2, something incredible happens. The model starts to develop what we call emergent abilities. It was never explicitly taught how to translate or summarize, but those skills just emerge from the sheer complexity of learning to predict the next word.
But after all this pre-training, the model is this powerful foundation of language. But it's unfocused. It can complete text, but it doesn't know how to follow instructions or be a helpful assistant. It needs a purpose, and that's where fine-tuning comes in.
This really leads to two main paths. We can create a specialist by training it on one very specific job, like detecting spam emails. Or we can create a generalist assistant, like the ones we use every day, by fine-tuning it on thousands of examples of instructions and helpful responses. This is what really teaches it to be a useful conversationalist.
And what's really efficient about this is that you don't have to retrain the entire billion-parameter model. A technique called LoRA, or low-rank adaptation, lets us freeze the huge original model and train only a tiny set of new parameters. We're talking sometimes just 2% of the original size. This makes powerful customization accessible to pretty much everyone.
And so we land right here, at the billion-dollar question that is defining the entire AI industry. Do we just keep building bigger, more powerful general models, or is the real future in creating highly efficient, specialized models through clever fine-tuning? The answer isn't clear yet, but whichever path wins out is going to shape the next decade of this technology.